Okay, so welcome back to the lecture series of finite volume, and where we will continue our discussion where we left in the last lecture. So, the computational overhead increases substantially, because all the phases now actually start storing all the component of the velocity field. For example, if you look at this phase, this storing this component, also this component. Similarly, this phase store both the component, this phase also. So, each phase stores both the components of the velocity field. Now, the problem is further complicated in this case of an unstructured grid. So, this is still a regular grid, but in a curvilinear system, but when you have an unstructured grid, there you can get more problem. Now, in that case the unstructured phase you do not have any staggering direction. So, unstructured grid, no specific staggering direction which can allow you to do that, and only way for staggering concept to apply is by changing the size of the cell elements, which was used for pressure and velocity component. Now, finally, what happens that the geometric information is also stored and more than the doubled when you go like this kind of arrangement increases the computational overhead like anything. Now, which turns out when you see all these advantages, disadvantages, or rather pros and cons of all these, it turns out that the collocated grid system is quite attractive. Collocated system where everything stored at cell center is found to be quite attractive, and that is what I mean, lot of CFD codes which are on finite volume, they prefer to use cell centered collocated grid system. But one can note that while the velocity components are stored at the centroids of the elements, as in the case for pressure or any other variable, the mass flux or scalar flux, scalar value in a collocated grid is stored at the element faces. So, the like this, the mass flux can actually be viewed as a contravariant component, except that is the case it is computed using a custom interpolation of a discrete momentum equation, which is known as Riccio interpolation, which is one of the famous technique which is used in collocated arrangement. And using this interpolation, you can actually you have everything at the cell centered. So, it is a cell centered collocated arrangement, and then you get an using this interpolation scheme, you get the fluxes interpolated at the faces. So, that you can avoid the problem of the checkerboarding issue. So, this is what the Riccio interpolation does. Now, the thing is that the deficiency in the original collocated formulation, which is the primarily the checkerboard or zigzag flow field, zigzag flow and pressure field, these are now can be avoided using this interpolation. Now, this one can see how one can, now it is essentially an equivalent to constructed a in this particular arrangement. Now, you see we taken one dimensional tensile and everything is stored at cell centered, and these are the flux components, and we use this Riccio interpolation. Now, this Riccio interpolation or Riccio interpolation what it does, or in this particular method what it does, that it actually construct a pseudo momentum equation at element phase with its coefficient linearly interpolated from the coefficient of the momentum equation which are based on the cell center. Now, how it is mathematically done? So, you start with a cell C and the downstream cell F, and you write UC plus HC equals to BCU minus DCU del P by del X at C. Similarly, for F, this is HFU equal to BFU minus DFU del P by del X at F. So, now if UF is the velocity equation similar to this equation, then the pressure gradient linked to the local neighboring pressure values can be seen here, and UF can be written as HF U equals to BFU minus DFU del F by del X at F. So, what now, since it is in the collocated system, so the coefficient of this equation, this particular equation, if you look at it, this is at the phase. So, the coefficient of this particular equation cannot be computed directly because it is in the collocated arrangement and all the values are stored at cell center. So, since they are stored at the cell center, you cannot do this. So, they are approximated by some interpolation from the coefficients of the neighboring nodes. So, you use some sort of a linear interpolation profile, and there you can get HFU equals to half of HCU plus HFU, which is, one can think, HFU bar. Similarly, BFU, which is half of BCU plus BFU, which is BFU bar. DFU, DCU, DFU, DFU bar. So, you use these values into this equation, and what you get an pseudo momentum equation which is written as UF plus HFU prime BFU prime minus DFU del P by del X F. So, this is in all practicant sense the momentum equation on a staggered grid. So, if you look at this particular equation, what this is, I say it is a pseudo momentum for collocated arrangement or system, but if you look at, this is equivalent to an momentum equation on staggered arrangement. So, by doing this kind of interpolation, what we essentially do, we actually transform the equation system to a such system where you get a similar staggered arrangement, I mean similar equations which looks exactly like an staggered arrangement. Now, in this one, the between the C and F, one has to obtain the linear interpolation. So, any variable which lies there in between F can be calculated as like this plus G F like this. So, use some sort of an where G stands for geometric interpolation factors. So, it relates to the position of the face with respect to C and F. Now, we can rewrite Hf by U, which is half of minus UC plus BCU minus DCU del P by del x C minus UF BFU minus DFU del P by del x F, which is minus UF prime DF prime del P by del x F prime plus BFU. Now, if you look at the coefficients, this could be of second order. So, one can see that. So, this is my del P by del x at F minus DFU by del P by del x at F, which is half of DCU del P by del x C plus DFU del P by del x F minus half of DCU plus DFU into half of del P by del x C plus del P by del x F, which is equivalent to 1/4 DCU del P by del x C minus del P by del x F, which is there, plus 1/4 DFU del P by del x F minus del P by del x C, which would be second order approximated scheme. So, this shows that this is also a second order approximation. Now, what we do, we get this one and then we put it back in the pseudo momentum equation. So, we can have UF equals to minus HF plus BF minus DFU by del P by del x F, which is UF bar minus bar del P by del x F minus del P by del x A bar. So, this is the average velocity and this component is some sort of an correction term. So, one can think of that way that now if you have a, so this is in one dimensional, if you have multi-dimensional, now multi-dimension you get V and Z component. So, you can write similarly Vf equals to Vf bar minus dA V bar del P by del y at face minus del P by del y face bar, which is like that. WF equals to WF bar minus del P by del Z F minus del P by del Z bar F. Now, what happens, you can see the equation system that you can, now all these equation, this one and this one, for 2 to 3 dimension one can write in a some sort of an vector form. If you write in a vector form, you can write Vf equals to Vf bar minus df V bar delta Pf minus delta Pf bar, where df V bar equals to a matrix which is df u 0 0 0 df V bar 0 0 0 df w bar, and delta Pf is calculated as delta Pf bar plus Pf minus Pc by dCf minus delta Pf ECF, and this is ECF. So, this is the term correction to interpolated phase gradient. This already we have seen while dealing with the unstructured grid system, and especially in the diffusion system we have done this calculation. Now, where CF is the direction formed only from the adjacent cell values Pf and Pc. So, we calculate del Pf dot ECF, which is del Pf bar dot ECF plus Pf minus Pc by dCf minus del Pf dot ECF dot ECF, which will get you back Pf minus Pc by dCf, where the phase velocity is closely linked to the pressure of the adjacent cells. So, here you can avoid the checkerboard problem. Now, before we derive the multidimensional momentum equation and multidimensional pressure corrections equation, so one can look at the some sort of an discretization of the momentum equation or the discrete momentum equation. So, let us consider this element, which is a very standard element, unstructured element, and element C, where the cell center is there. Then you have all these 6 surroundings elements, then you have these faces, this face, this, all these faces are there. These are the surface vectors which are normal to those faces, and the momentum equation you write in this fashion: del T of rho v plus delta dot rho v v equals to minus del P plus delta dot mu delta v plus delta dot mu del v transpose plus A B source term. Now, you want to discretize this one within the time interval t minus delta t by 2 to t plus delta t by 2. Now, one can basically take the volume integral and then convert them to a surface integral as we have done. So, if you go about that way, then we look at first individual term by term system. So, first look at this term, which is essentially del dot mu del V transpose dV. If you convert that to surface integral, it is mu del V t dot ds, which will be surface integral of NBC mu del V transpose dot SF. Now, the expanded form of del V transpose dot SF or SF in a 3-dimensional coordinate system, one can think about this would be del u by del x SF x plus del u by del y SF v plus del u by del z SF w. Similarly, del v by del x SF x del v by del y SF v plus del v by del z SF w, and del w by del x SF x del w by del y SF v del w by del z SF w. So, this would be x y, not v, just make a note here, this is surface vector. So, this would be S f x, this is S f y, this is S f z. So, along this column barabar they are same, it is a surface vector which is a component of S f x I plus S f y j plus S f z k. So, when we take the dot product, it will be all y j k. Now, similarly, we can look at the pressure gradient term, which will be delta p c v c, and when we transform it to surface integral, this will become essentially del v c p dot ds, which is summation over all the cell faces P f S f, and body force term, which is also a volume integral, which will be written like that. Now, one can use for the time integration, if we use the first order Euler scheme. So, first order Euler scheme if we use and discretize the unsteady term, and for convection term we use HR scheme, which is higher order scheme, and it is implemented HR scheme with deferred correction. So, which can be taken care of the, and decomposing the diffusion flux, which is implicit part aligned with the grid and explicit cross diffusion part. So, diffusion will have implicit component plus explicit component, that means this is aligned with the phase and this is cross diffusion term. Then the discretized momentum equation would look like discretized And by the way, you can note, or one has to note, that all these discretization process we have done separately, and that is why I have been telling, when we come down to the fluid flow solve problem, individual component integrations and discretization, they are taken care of. So, this we all separately discussed, and now we will put together things for the momentum equation, and which will look like AC V Vc plus summation over NBC AFV Vf equals to BCV. Here V superscript stands for the vector, and here the coefficient flux are given by ACV is flux Cc plus surface flux, or the summation over phases flux Cf, and AF, which is flux Ff, and BCV, which is given as flux Vc minus summation of F NBC flux Vf plus summation of NBC mu F del Vf transpose dot Sf minus del Pc Vc, where you can have the term like flux Cf equals to m dot f 0 plus mu f uf by dCf, which is convection contribution, this is your diffusion contribution, and flux Ff equals to minus m dot f 0 minus mu f by dCf. This is again convection contribution, this is again diffusion contribution, and flux Vf equals to minus mu f delta Vf dot Tf plus m dot f Vf HR high resolution skip minus Vf upwind skip, and we can compute other two term, which is like Cc equals to rho c Vc by delta T, and flux Vc equals to minus rho c naught Vc by delta T minus C Vc. So, this is how we calculate individual term, and we will stop here today and take it up from here in the next class. Thank you.